Okay, we just get a little bit more that we're going to cover out of Chapter 9, the rest of Chapter 9. Part of it we won't get to, but the rest of 9.2 it deals with 64-bit mode, easily scalable, so what you've learned will definitely scale to that. I mentioned at the beginning of Chapter 9 that there was one instruction I was going to show you that transmitted data from a floating point register into one of the CPU registers, and we're going to go over that now. So status word, remember we said that in addition to the 8 80-bit floating point stack registers, we also had several other registers, one of which was the status word. So remember when we compare, according to the results of the comparison, several of the bits in the status word, C3, C2, and C0, bits 14, 10, and 8, respectively, will be set or cleared according to those results. So how do I get those in some form I can use? Well, this is how we're going to do it. This is really cool. So first one is float store status word. Okay, float store status word is going to copy the status register to memory. So status word goes to memory, and then I can access it from memory. The other one is for storing the status word in AX. Okay, there are similar instructions available for the control word if I need to get to those bits, but for now the status word is what we're interested in. So let me show you an example that may come in handy. Let's say we're comparing two values, ST and ST1. The bits C3, C2, C0 are set or cleared according to the result, but that's in the status word. So what I want to do is I want to store the status word into AX. Okay? At that point, they are in AX, same bit number. So if I look at the bits in AX, oh my. Okay, here's bit 0, 7, 8, all the way to 15. Remember we said that C3 was bit 14, and we said that C2 was bit 10, and we said that C0 was bit 8. In the next instruction, this shifts. Once we've moved it into AX, we want to shift AH, which is this portion of AX, into E flags. Okay? So what it's going to do is it's going to shift the condition bits to flags, shifting them over by 8 bits. So what's going to happen when we do this is in E flags, if I look at the least significant byte, remember we have carry flag here, parity flag here, 0 flag, sign flag. Sign flag, we're not going to see anything. It just so happens when we shift these 8 bits to the lower or the least significant 8 bits in E flags, C3 corresponds to the 0 flag, C2 corresponds to parity, C0 corresponds to the carry flag. Okay? So, this instruction copies AH into the low order 8 bits of E flags. Okay, making it possible now for us to use conditional jump instructions. Again, because we have nothing going on with sign flag or overflow flag, this is going to make sense for unsigned mnemonics only. Okay, hopefully that makes sense. All right, let me do one more. If I have it on here, I may not. I got rid of it. So I'm going to go back because we're not going to go over this. It's kind of interesting. You can certainly do it if you want to. But for us, I want to just say that if, for comparison in 64-bit mode, SAHF or Shift AH to the lower 8 bits in E flags is not available. But it turns out that two instructions, FCOM-I, ST and ST number, and FCOM IP, ST number, will directly set the flags in the flags register for 64-bit machine. So you might want to try that on your 64-bit machine. All of this, or these two rather, may not be necessary because these two instructions will automatically set the status bits, or the ones we care about, in particular the 0 flag and the carry flag. All right, that is it for Chapter 9.